So we're fleetwood Mac.
All right, there we go.
So today we are going to primarily talk about the test and review for the test, and it can be as much up to the end of the class or as little as you want. So on my printer at home, yes. No. On my printer at home is a stack of 24 double-sided exam study guides.
Yay!
That doesn't do us any good, does it? So I just wanted you to know that if you go to the Canvas site and click on Pages and then Exam Study Guides, you will find an exam study guide. So anyway, we're going to talk about this today. We're going to go through it and answer questions that you have, make sure that you are feeling good about, well, I don't know if we're going to make sure you feel good about it, but anyway, we'll make sure I feel good about it. So here is a larger version. So some things to know about the test. It is designed, it's going to be in class on October 31st. If you're taking it at DAC, it's listed right now as any time on the day of the exam. If you need to go outside of that because of other constraints, please talk to me. It will have approximately 7 medium answer questions. By medium answer, I mean they're not one sentence or one phrase or 2 sentences or 2 phrases. They are more of a display of knowledge than that. But, you know, 4 or 5 sentences or 2 really good sentences that super show your understanding of what it is. In addition to that, there will likely be a matching section on terminology, and there may or may not be some multiple choice. People like multiple choice, but it means that they have to be somewhat tricky or they're stupid. And if they're somewhat tricky, then it's easy to choose the wrong one and get 0 when you actually knew something. So it doesn't do a fantastic job of testing your knowledge. It does a better job of testing your ability to take tests. Which is a good skill for some things. No notes, internet, phone, Canvas, outside resources this year. So none of that. Yeah, you're not solving any numerical problems, so you don't really need a calculator. But the equations that are on the study guide will also be on the test. So if they help you to remember something, remember, you know, a relationship or what's the most important thing, they will be on there. Questions? Excellent. Good. We're off to a fine start in our understanding. So, need to make sure that you understand stress, strain, strength, and the differences between them. This will be important on the test that you answer carefully using the correct term. Because if you answer on the test and you say everything with strain when you really meant stress, it's not the right answer. And so then I have to discern whether you just wrote the wrong thing down or whether you don't actually know what you're talking about. And that's pretty hard to do. I'd like to give you the benefit of the doubt, but it's important to make sure that you know those pretty well and that you feel confident in the differences between those. Engineering stress and true stress and why we need both of them is pretty important. So knowing that engineering stress gives us some important things. What does engineering stress give us that true stress strain doesn't? Yep.
You don't need to take nearly as many measurements to be able to get a useful stress strain diagram.
Okay, so it's less expensive. Yep.
Gives you the modulus.
It gives us the modulus of elasticity because it gives us a really good linear region in the elastic, which is where most design happens. So from a design standpoint, super useful. All right, what else does it give us? It gives us one super useful but odd other thing. Remember? Yeah.
The part where like goes down at the end of the graph.
Well, the peak of the graph, or the ultimate tensile strength. So it gives us ultimate tensile strength, That is the onset of necking in the part. And while it is physically meaningful that it's the onset of necking, numerically it is odd because we haven't been measuring the cross-sectional area, so it's not quite a real number. However, it comes up in so many properties and equations that we need to use. It's a highly relevant number, even though it's a little odd how we got there. Make sure you understand the constancy of volume and how it's applied to the different processes. Yes?
Sorry, I just want to double check the like modulus and the ultimate tensile strength. That's for engineering stress and strain?
Yes.
Okay.
Yep. They come from the engineering stress strain. So that's why we like them, because they come from that graph. The true stress, true strain never stops rising. And so there isn't a point that is the ultimate tensile strength. The stress keeps going up and up and up as there is more strain. Okay. Understand constancy of volume and understand how to apply stress and strain and constancy of volume to the different processes that we've talked about so far. You should know toughness, ductility, hardness, notch effects, or crack propagation. Any questions about any of those? Definition, usefulness, yes?
Like notch effects, is that like a part where getting like a notch is carved into it, like what like damaging effects that has, or what like
So that's
exactly?
so that notch effects and crack propagation are the same concept, and that is that if you have something in your part that is like a notch or a crack in there, the longer it is or the smaller the radius it is, the more likely it is to propagate through the material. And so if you have a process that creates a surface that has cracks in it, and then you either load that part in tension, or especially if you load it where you're continually loading and unloading it, so you have fatigue going on, then that's really dangerous. And so then you need to do something to reduce that. But we also see it in other places, like we see it on the structure of a material when we talked about austenitization. And if you cool the material really quickly, you get this super brittle, hard material. Well, some of the reason that it's brittle is because it contains these little sets of collections of carbon that have very sharp ends on them, internal to the part. So when you load it, those ends of those little sections are very small radius notches, and so they will propagate a crack or a dislocation through the part, cause it to brittly feel. Any others? You happy about those? Do you know how you measure them? Good. Okay. Excellent. Know what happens to a metal and its properties at different temperature ranges. So when we look at cold work below 0.3 times the melting temperature, warm work from 0.3 to 0.5, and hot work from 0.5 above 0.5 times the melting temperature, what happens to the material in each of those ranges? So let's talk about that. What happens in the cold work region? What do we have a lot of and not a lot of? A lot of strength, not a lot of ductility, okay? In the hot work region, we have the opposite of those. We have a lot of ductility, we don't have a lot of strength. The warm work region, well, it's just hard to tell. We might. So we can take things there when we do recovery. We can take things there and maybe we can regain some ductility and retain our strength, but we have to be really careful how hot it goes. The closer we get to the hot work region, the more strength we lose. We talked about heating of materials. So far we've just mostly talked about that kind of in the theoretical. We haven't applied it very much, I guess maybe casting. And then understand that expansion of a material with heat depends on original length of the material. So the longer the material is, the more it will expand, and also the amount of heat that you apply to it, the amount of temperature change, and then also different materials expand different amounts. All right, where is the biggest places that you deal with thermal expansion in plastic world? Sorry? So injection molding is huge because the injection mold, as the plastic shrinks and cools, it will shrink away from the walls if you design them correctly so that you can get the part out. The other place is in composites, where the composite plug, if you're putting it into the autoclave and you use a steel plug, the plug will grow 10 times more than the composite grows. So then your part will end up the wrong shape because your plug will grow, the part will cure there, the plug will shrink, and it's easy to get off. So that's a good thing, but your part is not the right shape. And so because of that, we have to use materials that have a really low thermal expansion. And those materials are super expensive because of what is in them and because of what it takes to machine them. They are just brutally expensive to machine. Very, very hard. Okay, good, happy?
Super
Questions?
happy.
Super happy. All right, my work here is done. Yeah?
What's the unit for toughness again?
The unit for toughness. Toughnesses. Let's see, what is the unit for toughness? So it's the amount of energy, it would be joules, because it's the amount of energies that something can absorb before it fails. So, yes, it is the area under the stress strain curve. So you have a stress strain curve. It's a plastic part, I take no responsibility for that. That area under there, up to the failure point.
The magnets are metal though.
No, the magnets would be ceramic. But the board that it sticks to is metal, so yeah.
Wait.
Ceramic
It's okay. I would imagine they are, if they're good magnets. Maybe they are metal magnets, that's why they're lousy. Yeah. Okay, any other questions? All right. Yes,
So,
put it
on the bullet point above where you are,
above where I are.
where you, what is sensible and latent?
Okay, so sensible is something just getting warmer. So it is putting heat into something and it gets warmer. So how much heat does it take to heat something up by a certain amount, a certain number of degrees? Latent is phase change. So I'm putting a bunch of heat into something, putting a bunch of energy in. It's not changing temperature, but it is changing phase. So it's either melting or it's turning into a gas.
The temperature's not, you just said the temperature's not changing?
Yeah.
The latent phase?
Yeah, the temperature is not changing. So if I have a pure material and I heat it and I heat it and I heat it, while it is melting, its temperature will not change.
Okay.
If it's pure material. If it is multi-component, then that's not true. Okay? How does metal solidification happen? How does metal solidification happen? By cooling, okay, so excellent. So we have a macro view. Let's go microer. What is happening internal to the material as it is cooling? In solidificationing. Yes?
The atoms are stacking on top of each other.
The structure.
In crystalline structure, okay. At one place, at a bunch of places, at a bunch of places. So that's super important. All over the place, we have these little nucleation sites. And so right here, it will start to build its little crystal structure, whatever it is. And then over here, it will build its little crystalline structure. And then when those two run into each other, they're not aligned with each other. And so the grain boundary is kind of crazy. They will have a bunch of errors and places that motion can happen near the grain boundary. Yes?
What are the little sites called again?
Nucleation. Yeah. So what you end up with is you end up with the city of Bellingham, right? The city of Bellingham started with as 4 little communities, and when they grew together at each of the corners, the streets don't match. So then you get these weird mismatches that you have to figure out. So it's awesome that we live in a solidification. Yeah, so in this structure, is the structure perfect? No, not at all. There are all kinds of things that are imperfect about the structure. It has impurities in it. It has dislocations, which are just gaps where the thing didn't grow quite in the right order, and so it may have rows that just dead end, or it may just have a missing component. Yes?
That reminds me of, well, your video, I had a question from the extrusion thing. We quenched the metal and then used this word, and I don't remember what it was, but.
Timber?
No,
Age?
it was like, no, but it was like,
Okay.
it was just like all these, why did we quench it? My question was why did we quench it?
Okay, so it depends on what we're doing. So the reason that you quench is because you want to retain the properties that you got. So that is when you are hot working a piece of material. So like, especially if you are doing impression die forging where you're slamming the thing inside the die. We are forming the grain structure to the shape. And we're also putting in a tremendous amount of strain hardening. But the part is hot, so it is, as fast as it can, it is recrystallizing and getting rid of all that strain hardening that we just put in. And to stop it from doing that so that we can retain the strength, we quench it, which means that we dump it in oil or water or air.
Why would you do oil?
Different materials do better with different things that they're quenched in. So water has the highest heat capacity of anything, and it can quench things too fast. And so you can use oil, it can't contain as much heat, and so it does a slower quenching of the material.
And when you quench it too fast, will it get brittle?
Well, when you quench it at all, it gets brittle. But you can control the rate at which it quenches, and that will control the amount of diffusion of the interstitial that can continue on as it is cooling. And it helps you to set the ductility or the strength of the material.
Thank you.
Is that good?
Yeah.
Yes?
What's the carbon scale that comes out of like quenching? Does that come out of the material where it was like drawn out? Or is it?
The carbon scale, I think, comes from the material on the outside just because it was hot work, and so it is reacting with everything that it can. It's reacting with the air, it's reacting with the oxygen in the water, it is reacting with the oil, whatever it's doing, it's reacting with all of those. So I think that's where it comes from. Good? Questions? Happiness?
So much
Have you
happiness.
figured out what I don't know about a polymer?
What?
For the name of a group of students, just a little lame.
But then each
Chain.
student is a monomer.
I
And then
I
they become a polymer.
I understand the concept.
Yeah. You just don't like it.
I don't know.
No, he's right.
It's a little self-referential and not quite cool enough.
Gil, if you come up with a name for us, we will adopt it.
Well, I wouldn't
We'll
promise
change
that.
Well, it has to be cool.
Oh,
It has
okay.
to be cool.
All right.
I mean, I would promise personally.
All right, so you should know about the irregularities that happen in a crystalline structure and what they're good for and what problems they cause, because they do both of those. You do not need to know stuff like what does a face-centered cubic or body-centered cubic or hexagonally close packed structure looks like and what are the 6 slip planes that go with it. That's so materials class. We don't need to know that right now. But what I would like you to know is what's happening at those slip planes. What's happening when dislocations move and what stops them from moving and what effect does that have on the macro properties of the material. Yes?
Wait, what does stop them from moving?
There are several things that stop dislocations from moving. One is when they hit another dislocation, they may not be able to continue on. Another is when they hit a block of impurities, whether they be interstitial or substitutional. And then the last is when they hit grain boundaries. And the difference between those is that if it hits another dislocation, we can probably get it to form more by putting more stress in. We can get it to continue on. If it hit a set of impurities that are interstitial, then we can reset that by going to the range of recovery, where we heat it up to the warm working region and we disperse those interstitials, and then that's the way that we gain some ductility back and we're able to form the part more after we recover it. But the grain boundaries, we can't do that without going to the recrystallization phase. So we have to go to hot work or to go up to the hot region where we start to recrystallize the material, and then that grain boundary will no longer be relevant.
So you want us to know what happens at slip planes?
Yes.
And how dislocations are, like, stop, and then how the dislocations affect our material properties?
Yes. Yep.
So just to clarify, it affects the properties by like increasing the strain, or?
Well, it limits more strain from happening. So if you have dislocations intersecting each other or intersecting any of those other things, then you can't continue to strain the part without adding a lot more stress. So that is strengthening or strain hardening of the material. So it's increased your strength, reduced, well, maybe not your strength, it's increased the strength of the material, reduced the ductility of the material, and that's either good or bad depending on what you're planning to do with it.
And we should be able to explain why.
Yes. Yep.
So for impurities, to get past that, we would heat or do more hot work on the part to get.
Well, it depends on which impurities. So if it's interstitials, you can go to the recovery range and you can diffuse the interstitials. And you lose a little bit of the strength, but you gain a lot of ductility. If it is substitutional, you probably have to go to the hot work region to reform the structure to get them to move. Some substitutionals will diffuse, but it takes a lot of energy to get it to happen.
Gotcha.
All right, phase diagrams. Make sure that you know the 3 kinds of phase diagrams. What are the 3 kinds of phase diagrams that we've talked about? What is a phase diagram that we've talked about? Which one?
It's like the one where you have like different amounts of certain materials, like 2 of them, and then like the percentage of them, like how their melting point changes based off the thing between them. I mean, not just the melting point,
Okay.
all of its points.
Yeah, so that's actually 2 of them that you talked about there. Because remember, I have something and I've got 0% of one and 100% of that one and whatever the other one is. And so I will have some phase diagrams that look like this. And this is just 2 materials, but not a eutectic. And so what is this line called?
Which one?
This one.
Solidus.
The solidus line, this one? Liquidus line, and in the middle?
Slush.
The slushy zone, that's right. Right? Okay, so the alternative to that is, well,
And that's just one material.
is two materials.
Oh, this is two materials.
Because we're varying the percentage. If it is one material, then it will, the diagram will look like something like that. And what this is doing across the bottom is temperature on this one, and this is like liquidity or something. Anyway, so, well, no, this is temp. Never mind. Temp. Yeah, it's just something else. Anyway, this section right here is the melting zone. So this section corresponds to this point on this graph over here. On this graph, because we're varying percentages, it is just this one corner where we see it is 100% of one of the components, and so it has a single melting point. When we move across here, we get these weird melting points that are kind of separated by the slushy zone. Over at the other end, where 100% is, we have the other melting point for the other material.
Gil,
Yes?
is the slushy zone like an actual scientific term, or is that just something you say?
No, it's real.
It's like a real topic.
It is a real scientific term.
Is it slushy zone?
Yeah.
Okay.
They don't call it the Slurpee zone, which is really too bad. It would be way cooler, but I think
I think it
Slurpee
makes
is owned by
more sense.
7-Eleven.
Is it trademarked?
Yeah. Darn
Bye.
7-Eleven. And then remember, the other kind is the eutectic. So the eutectic is similar, but it kind of looks like that. And so the eutectic has this one place in the middle, this 1% at which the melting point is lower than either of the constituent materials. Again, we have the slushy zones in here, where it's partially liquid, partially solid. Down here is all solid. All up here is all liquid. And remember, these sections on the end are the solid solutions. So the material is all solid in these, but it is a mixture of the two materials where you can't tell them apart. They're completely in a solvent solute state. Whatever that is. Anyway, solution. Yeah. It's hard to describe a solution without saying solution. Anyway. All right. Are we good with that? We happy? Okay.
So happy.
Liquidus, solidus, interstitial, substitutional, diffusion. All right. Austenitization was not moving to Austin because there's a lot of traffic there. Frankly, it's a miserable place to live right now because there's a lot of traffic and it's really hot. And a lot of people. Did you go to college or you thought about it? I did go to college in Texas, but not at UT Austin. I went to a good school.
Yeah, that's the shade in Texas.
I only say that because my parents went to Rice, my nephews went to A&M, and my dad went to UT Austin. So anyway, but I went to the good one.
You went to the good one.
Actually, my brother went to the good one too. So
Two?
anyway, two of us, yeah. It was awesome.
Go again.
Would you like to hear about the Red Raiders? They have a horse. I mean, that's super cool. Every time they score a touchdown, they ride around the track really fast on the horse.
Yeah.
That is
With
pretty cool, actually.
not holding onto the reins, but the reins in their teeth, and they ride around holding the guns up. It's pretty awesome until they wipe out on the corner and break the horse's leg, which has only happened once that I know of. But anyway, that was sad. I was not at that game.
Did it happen while you were there?
It was the year after I left.
It's because you left.
I know.
You made it happen.
Anyway, that was quite an aside that did not help us. All right, austenitization. I know there was a point to this. Yes.
What is this? What is
Had a
the
good
point
run.
on the right side?
This point?
The other one to the right.
That
The
one?
melting temp?
Yeah, so this is the melting temperature of 100% of that constituent.
Okay.
And this is the melting temperature of 100% of this constituent. And then in the middle, it happens somewhere in this region across the melting temperature. It's not a single temperature, it happens across that region of temperatures because some of the material is melting and some of it is still solid.
The shaded area is the slushy area, right?
It is,
Yeah.
the slushy area, yes. Excellent. These, right, if I can draw that little dog, I would, but I can't, so I won't. All right, austenitization. You're just making me say it a lot of times. This is really cruel. Okay, I don't need you to know the separate paths, right? There was a ton of different paths, but what I need you to know about austenitization is what? What is it, what we care about with it? What is important to us? There are a lot of things, so. Sorry?
How two steels is exactly the same amount of,
Okay, yes, how do two steels with exactly the same ingredients have totally different material properties? Okay, how does that happen? Yes?
Based off hot work or cold work?
Not for austenitization. So the cold work can definitely do that, but not as far as this is concerned. That is another path to two different sets of properties. Yes?
Just by changing the crystallinity?
Okay, changing the crystal structure, yes. So we can go to what we're doing in austenitization, we're going to a very high temperature, and we're allowing the crystal structure to reform in the material, and then we are cooling it at some rate. And the rate at which we cool it will define how the interstitials and substitutionals are distributed throughout the material, and it will define the grain size. If we cool it very, very quickly, then we have a hard material that is very strong but super brittle. And the shape of the little groupings of interstitial atoms will be such that they cause fracture to happen. So to get around that, after we have cooled it quickly, we can heat it back up into the recovery region for a while, and we can allow those to disperse some, and that will allow us to gain some ductility back.
So is it kind of just like the rate at which you cool stuff? Like the rate at which you heat it up doesn't necessarily matter. It's just you're bringing it up and then however fast you let it go back down.
For what we're talking about, we'll say yes. It actually does matter, but for metallurgists to know, we don't need to know. You don't need to know, I don't need to know.
Is reheating it back up also part of the austenitization process? Or?
Yes, so that's called normalizing or annealing, when we heat it back up and distribute things and then cool it back down. And so we can get lots of different shapes and sizes of the distributions of interstitials, and depending on how we cool it and what our temperature process is. And if you remember, there were all kinds of wacky things you could do. I almost knocked the chalk tray off again. Very gentle on the chalk tray. So as you cool the material down, you can drop it straight down really fast, get a hard brittle material. You can drop it down and then you can oscillate it for a while and then cool it slowly. You can cool it super slowly, that's bad material, don't do that. You can also do things where you drop it fast and then you heat it up to a lower temperature and normalize it. There are many, many, many different processes depending on what you're trying to do. But it is all about the size of the grains, the shape of the grains, and the distribution and shape of the impurities that are inside it. Questions? Happiness? Yes?
So when you heat it back up to recover, you're dispersing the interstitials? Is that
Yeah.
what you just said?
Yes, you're allowing the interstitials to diffuse so that they will take on different shapes of globbing together and different distributions throughout the material. Cool. All right. Great. That was making me think that a group of manufacturing students could be like I don't know, something about the shape of an group of interstitials. I'd have to think about that a little more.
It could be a mill, cause they mill around.
A mill is pretty good.
They could be a mill, but there aren't multiple things in a mill. It's just a mill, and we've got a lot of them. So we need a name that has a lot of them.
It's not like, oh, it's not.
Okay. Why do we do casting?
To make parts.
But why casting? We can make parts a bunch of ways. Why casting?
Oh, it's cheap.
It's cheap, it's easy, it's quick. What are the problems with casting?
Bad parts.
The surface quality is trash, the interior quality may be trash. It will, yeah, I don't know. We'll find out this afternoon and Thursday afternoon when we break our parts out and see what they look like.
Yay.
Maybe they'll be great. Maybe we will be amazed.
I bet we will.
Yes.
You seem not very confident, yeah.
You're saying
I
a lot
have-
of maybes.
I have a lot of a lot of years of failure in this category.
But this year will be successful.
But this year could be the one.
Do you have any years of success?
Yeah, I mean, we've had things that have worked across time, but we've also had a lot of things that have a lot of learning opportunities. You should be able to know, or you should know the parts of a mold and be able to speak of them correctly.
All molds, like every mold we've worked with. Oh, like just like B mold or like.
In general, I think.
The list of things that's listed right up there, under the second bullet under casting fundamentals. You should know those things, and you should know why we would use them. Why would we use a cavity, or a chill? Why would you use a chill? Yes?
To control where the solidification of the casting part starts.
Okay, and that gives us, why does that help us?
So it doesn't start crystallizing at the wrong spot, potentially causing the mold not to be filled properly.
That's right. So if it starts to freeze at the wrong location, then we can't refill the material when it shrinks. So we force it to start at one location and work its way out from there so we can continue to refill from the risers or the sprue as it fills as the part shrinks. Yeah. Do you have a question also?
Yes,
Okay.
I don't remember, is the chaplet, is it used for support?
So the chaplets are the little things that are made of the same material as the final part, and their purpose is to support the core. So this core is fairly small and fairly light, but even so, if you're trying to support this with sand, it could still not be at the right location. So you use little pieces of metal to support it at the right place within the mold until you get the material in there. And it will, the chaplets all get melted out, but by the time they get melted out, you have metal all around the thing. So then actually your problem at that point is that the core wants to float because it's lighter than all the metal. And so the problem has reversed, but anyway, that's fine. Yes, understand all those things. Be able to speak of them correctly when you answer a question about a design of a mold or the parts you might use. Yes. Alexa.
Okay, I was just gonna ask if this is gonna be like a label situation.
It could be a picture of a certain brown mold that you've seen in slides and you are matching names with positions, or it could be a question about how you address a problem in molding.
Have you written the test yet?
I have not written the test yet.
No.
I had, this week has been,
You should do the labeling one as a
This-
first.
That sounds better.
this week has been totally bazonkers.
Oh,
Bazonkers.
the second day.
I know. And it has me worried. Because I've only
Yesterday
gotten,
was the zonkers.
and early this morning.
Oh.
Yeah,
Until now.
I woke up at 1:30 thinking of all the things that I had to do today, so it's been a long day.
Uh-oh.
You should know what fluidity is, all right? And you should know that fluidity is only slightly less hard to say than austenitization. What does it depend on? remember that it's not just the metal or it's not just the mold. Anyway, for each of the ways that you improve fluidity, there's a downside. They all have a downside, so you should make sure that you think about the fluidity and what are the downsides of the ways that you increase it.
What are the ways you increase?
What are the ways you increase? There's so many ways. You can heat the mold. You can superheat the metal. You can make the walls smoother of the mold. You can use a different material that you pour, if that's allowed in the question, which it never has been so far in the questions that I've asked, but people continue to answer that anyway. Let's see, you can pour faster. You can increase the size of the runners. You can add larger risers and more vents. Hi, yes.
Hi, okay, so in the video you talked about how if you like sneak up on a part, it makes it more fluid kind of, or like easier, like push
Did
into
you?
something. Like the faster you push on it, the easier you can get it to go through both for cold work or a die for cold work.
Okay,
Can you re-explain
that's
Is that-
in cold, that's in reverse impact extrusion, in
Mhm.
forward extrusion. We'll talk about it when we get to
Is it-
extrusion.
Okay.
We're not there.
Are you saying forward or forward?
Forward.
Okay.
Forward, not Ford. GM, Chrysler, I mean Chrysler extrusion, yeah. I had a Jeep that extruded its engine.
Are you serious?
Yeah, it was kind of too bad. I went to test drive a Jeep. The guy said, "Hey, do you want us to drive your Jeep and give you an offer on it?" I said, "Sure." He drove it halfway around the block and it shelled the engine. I'm like,
What was their offer?
Nothing. They were willing to
Wait, was this
see how much it would take to fix it. Not the Jeep truck. It
Okay.
was the Jeep previous to this one.
Yeah, the Jeep truck.
We call it the Bleep because it's blue and it's a Jeep. We've also called it the Druck, but that's hard to say. That is neither here nor there. Why do we choose sand casting? Why do we choose investment casting? You should know the difference between them, why one of them might be chosen in a different situation. You should know the basics of the die casting process and what it takes to want to do die casting. Why don't we just die cast everything? Because it's faster. It is expensive, yeah. And we can only do it for low melting temperature materials because the mold has to be higher temperature capability than the thing that we are melting. And so it's just not economically feasible to make molds out of diamond, it turns out.
What?
I mean, it's sad, but it's true. Yeah, so, you know, if I gave you a scenario with a random engineer who was planning to make something, you should be able to tell them what method they should use to cast it and what they should be concerned about. All right, good. Slip, strain hardening. How do you undo strain hardening?
Heat it back up.
You heat it back up to either recover or to recrystallize. Make sure you know the difference between recovery and recrystallization, and you use those words correctly. Those are two that get interchanged when people are talking about them on a test in a high pressure situation, and that makes answers that are really confusing.
Is recovery like the interstitial points moving around and stuff, and recrystallization is like the new grain slowly forming?
Yes. So the way to remember it is recrystallization means that the crystals are changing, right? So so that's got to be hot work for the crystals to change.
Sorry, wait, what is recovery?
Recovery is when we go to this low temperature and we're rediffusing the interstitials out of the way of the dislocations. So we gain a little bit of ductility and don't lose much strength.
Recrystallization is like always hotter in our copper.
Yes, because recrystallization is back to the hot work region so that the crystals start to grow. Know what is good and bad about hot and cold work. What are the advantages or disadvantages of working in each of the regions? So there are all kinds of differences with energy usage and materials that you have to use to do it and how hard it is to get things to deform. Know your stress sag, right? Mostly with that, you need to understand that the point of the stress sag or the stress kite, depending on what your choice is. We're all welcome to have free choice, whether you choose the egg or the kite. But know that the point of it is it's how you evaluate something that is under combined loading. So you have loads from different directions, loads from different sources, and we're trying to understand how does the material react or what is required to deform the material when we have this combined loading situation. And then in some of the things we talked about, we should understand why, does that manufacturing process cause us to have a combined stress loading? And if so, is it making it harder to deform the part or easier to deform the part? Are there things that we can do about it to undo it if it's harder? Can we make it easier? Like in rolling. When you're rolling, the friction prevents the material from getting wider. So we immediately on the stress sag go to that 1.15 region. And so what can we do about that? Well, we can grab the end and we can pull on the end to put it in tension and we can get it back to where it only requires the flow stress to be able to deform the material. If we're doing cold rolling. If we're doing hot rolling and we grab the end while it's hot and we pull, we'll just rip it right off. So it won't help us. Questions about those?
Why do we do hot rolling and cold rolling in which situations also?
What do you think?
Ductility?
Yep. So if we need to deform the shape a lot, then we need to have a lot of ductility, then we're gonna do hot rolling on it. And then when we get to the point where we want to do the thing, create the final shape, and we may want to impart some strain hardening, then we'll do that in the cold region. Also, hot rolling has the same problem as all hot work, that it's quickly reacting with the environment. The grain is growing really quickly, so the material's becoming weaker. It's not going to create square edges because the part's gonna shrink afterwards and change shape. Forging. Should know the terms upsetting, drawing, squeezing. In the context of bulk forming, you can know them in the context of a country song if you want to. Cogging, fullering, and edging. Think about those and where they put you on the stress sag. Why do we do those? Why don't we just squash the whole part at the same time? Instead, sorry? It's harder to do, but specifically, why is it harder to do?
Because you're trying to apply more force over more area.
Okay, more force over more area is one reason, but there are more. Why do we do cogging?
What is cogging?
Cogging is where we want to make this thing and we don't squash the whole thing at the same time, but we squash it a little bit. Squash, 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 moving along. Little tiny bits as we move along. Why do we do cogging? Yep.
To have more control over how the part is being elongated, so it's like squishing at the same time without having to just go out in all directions.
Okay, so we can control the direction that it deforms more, right? What else?
Except it loses less heat with like less contact with more metals.
Yeah, I don't know if it's interesting. I don't know if it would actually lose less heat because in the other one, you're spending less time overall.
Doesn't it have to do with like the crystallization as you move along, it starts to cool where it's already squashed, and then you come back and it keeps it.
Yeah, so you squeeze in one area, uh-oh. Acknowledge. Acknowledge.
Oh, the other one just went.
Everybody's phone is about to go. Yeah, as you are compressing this in these little bit areas, you compress it and it work hardens. It strengthens right there. And then you go and you squeeze the next area, next area, next area. By the time you get back to the beginning, because this is hot work, it has had time to recrystallize. So when you want to deform it, it has the full amount of ductility. So you can continue to drastically change its shape. If you did the whole thing at the same time, you quickly reach the limit of ductility, and then you would just have to stop and wait anyway. So why use the really giant press that would be needed to do it all at the same time if you're gonna have to wait anyway? All right, then no fullering and edging. Edging is pushing out towards the edges. Fullering is pushing to the middle, making it more full. So with a curved die. And the difference between those is the point on the stress egg. They're very different points on the stress egg. Impression die hammer, closed die hammer forging. Remember that one squashes the part into a particular shape in a small number of slamming it together. It uses flash, or it creates flash. The flash has about 4 purposes. You should know what those purposes are, what's good and bad about them. And then remember there was a graph of what happened in the force as it was closing. The force goes up and up and up and then up really high. And why does it keep going up? There were 5 reasons why it kept rising. So one thing to talk about, this is a good time to remember that, just to make sure that we're clear. Yes, we're going to go back. So on the PowerPoint slides that are on here, when you look at the PowerPoint slides, let's see what it does when it's on here. Yeah, so you may want to download them because they have all of the notes in them. And I'm not sure that we can, yeah, it doesn't seem to want to show the notes here. If you download them and you open the PowerPoints have all of the speaker's notes. So if there's a question asked on a slide, it will have the answers to that question. So like on the slide where it talks about what are the 5 reasons that the pressure, the force increases in closed die hammer forging in the speaker's notes. It may have a little picture of a cloud. It depends on which browser you're using to look at it. It has a little picture of a cloud. You click on that and it'll show you the answers to the slide.
Which browser gives you the cloud?
I think Adobe Reader, and so I don't know.
What do you mean cloud?
There's a little picture of a cloud. Maybe it's a thought bubble. It's how you get to the speaker's notes. That didn't work. Feel better about that. All right. Questions? All right. Rolling. Remember why one side of the material is shiny? Mostly what you need to know is how rolling and the constancy of volume work together. You should not, you don't have to memorize the lyrics to Rawhide, but you can hum them quietly during the test.
Why would you need to?
Will you hum them to us?
Nope.
You put it on loop during the test.
Nope. Cannot do that either. Thinking about the effects that rolling has on a material, and the roll force, the radius. So as the material gets thinner, I have to reduce the diameter of my roller, or the radius of my roller, both of them, radius and diameter. What are the problems with that? with a roll is I'm reducing its diameter.
Just go faster.
Go faster.
Well, no, as it does have to go faster, but the bigger problem is deflections. Because I'm trying to squash this piece of material and now I have a little tiny roller and it doesn't have the ability to do that. So how do I address that?
More rollers.
More rollers. Just back it up with money. Stack money in behind it until it doesn't bend anymore.
Perfect.
Yeah, so that would be one way to do it. I think a really good question. So we did extrusion, we did drawing, and we did rolling. All of those can make the same shape part. Why would we choose one or the other process? So that's a really good thing to think about. Why would we choose to do it by rolling rather than extrusion or drawing? And because not every part can be made by any of them, but some parts could be made by any of them. Like the edges of the chalkboard, which were extruded, they could be made by rolling just as easily.
Hey,
Why were they done by extrusion?
is drawing or extrusion more expensive?
Is drawing or extrusion more expensive? Probably extrusion is more expensive because you're heating the part. I don't know. Yeah, probably. It's hard to say.
So you
The-
would never
the-
make us pick between them on the test, like?
I might. So, well,
But not for
because you
long
need to know, you need to be able to evaluate. So drawing, an individual step of drawing is relatively inexpensive. All it takes is pulling really hard on a piece of metal through a die that makes it smaller.
Yeah.
But the problem is, you can only reduce it in size by a small percentage. And so you don't draw once, you draw many times for a lot of things. And so if you're gonna have to draw many, many times, now it's a big process when the extrusion could have just been done on one machine. But that was kind of an expensive machine to buy in the beginning, so, I don't know. Economics, so hard. Extrusion. You should understand, so we had direct, indirect, hydrostatic, and then impact is a little bit different. But for the first three, what are we trying to address? What is the big problem in extrusion? What's the big thing that we have to get around? Friction, that's right. Friction kills us in extrusion, and actually kills us in drawing too. But all of these are ways of trying to get around or reduce the amount of friction so that the part will extrude with less force or extrude better. Sometimes the friction causes surface problems. So anyway, understand the different ways that we try to get around it. What is direct versus indirect? Hydrostatic, it's weird, don't use it a lot. Impact extrusion, super cool. So you were asking about what's happening in impact extrusion. The question for impact extrusion is, it's cold work usually. Why can the material deform so much? Because we talk about being limited to 20 or 30% strain on most processes, but clearly when they made the little medicine tubes or the Apple Mac Pro, it was way more than 20% deformation that happened on that material. It, changed shape drastically. Why can we do that? Well, it's a thing called superplasticity. So if you do a process fast enough, you can cause within the structure of the part, the material, or there will be localized heating and localized softening of the material, which allows it to deform superplastically, but it does not heat the part overall too much as a whole, and so it won't change the properties of the part very much. It's pretty neat. So there is a weird thing that happens. There's an intersection in the study of physics in what happens with materials that are changed in shape really quickly. And it has two applications. One of them is manufacturing, because many processes get to this point where you are changing the material so quickly that localized things happen in the material that are hard to understand. and the other is nuclear weapons. Because the process happens so quickly in a nuclear weapon, either crushing the core or the expansion outward, that in both of those there are superplasticity happening in the materials. And so there's this weird shared field of study where people are shooting materials at very high speed towards each other and watching the collision. It's pretty cool. So anyway, any questions about extrusion? We good? Feel like, yeah, we just did that. It's easy. Okay, happy, good. All right, drawing. Main thing with drawing is understand why drawing is done in many steps.
You can't deform 30%.
Yeah, 20 to 30% generally, depends on the material. But yeah, we can't deform it so much, so we have to do it in many small steps, and it's limited by the tensile strength since we're having to pull the material through the die. What are approaches to drawing? One of the approaches is you should have the tallest individual have the lowest job. That's really good ergonomically. Yeah. Okay, and then in the labs, you should think about how the labs have helped you to understand concepts that have been part of what we've done, and there is a list of the labs that are there that we've done so far.
Is there gonna be something like with the G code where we had to draw the house?
No, there will not be G code from the lab on the test. No.
Good.
I might ask you a question about G code in general, but not a specific thing. You'll learn G code next year,
Yay.
and I will expect you to be good at it.
Oh.
Because you made a house, that's right. So, what else is there to learn? I mean, you know practically all of the things that there are. Okay? These equations will be on the test in the form that they are, right there. And can be useful or not useful. Whatever you choose to do with it, they're just there for your reference if they are helpful. Questions?
How much is rent?
How much is rent? I don't know. The equation will have to, it says that interested equations are invited to apply. It doesn't say anything about plasticians. All right, if you are studying and you have questions, you are welcome to email me or Teams. Me? Teams? Maybe a group of plasticians is called a team. That would be boring. Anyway, you are welcome to send me a Teams communication to answer the question, and you can send it anytime, and I might answer it right then, or I might answer it some other time. Just a warning, if you send it really late, I tend to reply really early. So, it's okay, yeah. Yeah, turn your notifications off, that's all good. And test will be here or at the DAC. For lab today and on Thursday, we will be in the water jet room and outside. So we'll split the labs in half. Half of you will go outside and demold with Robert, and half will stay inside, and we'll do path planning on the water jet. Overall, you did a good job with your designs. There are lots of really good creative designs, and mostly the directions were followed. There are a few where we'll have an amount of work to do in repairing things. However, I've gone through and done the major repair. There's just the minor delete extra lines kind of repair that will happen on the water jet. But I think overall, really good designs. I think it will be a fun year for fidget spinners. Yay. All right, see you this afternoon. Or Thursday.
Another fun year. 7th grade was